questions about anything? No? So, what we're going to do today is mostly go over that paper, but you need a little bit of background in order to understand it. And so, the first half of the lecture is actually going to be the background that you need to understand what's going on in the paper. And so there are really two parts to that. One is the idea of Jacobian iterations, which is something that I'll explain in a moment. And then the other has to do with parameterizing rotations. And so I'll talk about both of these things. With regard to parameterizing rotations, you already know something about that, in that we've talked about Euler angles before. So Euler angles are one kind of parameterization of rotations, but what's used in that paper is something different, which is the so-called axis angle description of rotation. And I don't think we talked about that, or if we did, it was very briefly. So I'm going to talk a little bit about this, and then I'll talk about Jacobian iterations. And then by putting these two things together is basically what that paper is about. Well, on the surface, okay, what is that paper about? So you have a microsatellite, which is like a little box, and you have these little flippers, and you can rotate this flipper by some small angle, but you can't rotate it all the way around. And there are flippers on each side of the satellite, top, bottom, front, left, etc. So these guys can flip, and because they have mass, and because of the conservation of mass and conservation of angular momentum, because there's no outside force or torque acting on this, when this flipper flips like this, relative to the body of the body part of the satellite, then the satellite is going to turn in the opposite direction. Okay. So these flippers flip. The satellite turns in the opposite direction, and then they stay turned, and then flippers on one of the other surfaces flip. And that rotates the satellite a little bit in that direction. Remember, the satellite has already been turned a little bit because these flippers moved. Then while it's turned like that, these other flippers turn, and it turns a little bit like that. And then the third set does the same thing, and it turns like that. Now, if we reverse those flipper motions in the opposite order that they were done. In other words, you flip 1, 2, 3. If you do 3 in reverse, and then 2 in reverse, and then 1 in reverse, you're going to come back to exactly the same orientation that you started. Because, so it's basically a rotation, let's say, around the 3-axis by some angle, then around the 2-axis by some angle, and then around the 1-axis by some angle, gamma. So it's just like Euler angles, although it's not ZXZ Euler angles, it's more like roll pitch yaw Euler angles. If I then did this one in reverse, that would be R1 transpose gamma. That would just kill this one. If I did this one and then followed by this one in reverse, followed by this one in reverse, it would just return things back to where it was originally. And that would defeat the point. Okay? The purpose of this is to reorient the system. Okay? So And the flippers, you know, once you flip them to their hard stop, to the limit, you can't move them any further. So if you're going to reuse the flippers, you need to return them to the center of their range, the middle range there. And so the idea is you do these rotations, and then you return the flippers, which implements the opposite rotation, but you do it in the reverse order. So in other words, so in an order that actually, so that doesn't destroy what you just created. So we could do, for example, R3 by negative alpha, R2 by negative beta, R1 by negative gamma. And because this R3 is separated from this R3 by this stuff in the middle, this does not cancel with that, because rotations do not commute in three-dimensional space, right? So if I rotate around the x-axis, followed by rotation around the z-axis, and I do that in sequence, then these guys don't cancel each other. It's not like addition of numbers, matrix multiplication, the order matters. So now this, you know, we could have done it, you know, with these or in this order, as long as this is not directly next to this one, this is not directly next to this one, and this is not directly next to this one. And so this gives a rotation matrix that depends on these three angles. This is not the Euler angle rotation matrix, but it's still a matrix that depends on these three angles. Now for these flippers, actually, the amount of, because they're not that massive compared to the base satellite, these angles are generally going to be small. So you can execute sort of by one set, maneuver involving forward and reverse rotations of the flippers in this kind of order, you can maybe change the orientation of the satellite by a few degrees. But the idea then is that you then do this lots and lots of times. So you do flip, you know, then unflip, and then you end up with the satellite at some orientation, and then you do the same procedure again, and then again, and again, and again, and then eventually you change the orientation of the satellite by a larger amount. So this effect, if you do this n times, you know, then the effect will grow, okay? And so what the paper was about is if you have a particular target orientation that you want to reach, how much should you flip each of the flippers, and how many times should you flip them so that you can make the satellite eventually change its orientation to the specific one that you want to reach. And so you can think of this as, you know, these flippers are sort of humming like the wings of a hummingbird or a bee or something, and as they're doing their flipping and reverse flipping maneuvers, then the satellite sort of gradually changes its orientation. That's sort of the idea of the paper. And so how do we do that? Well, we need to understand these two things right here. Okay? So, any questions about that? So this is an alternative to what is commonly done in satellites. So we talked about gravity gradients before, right? So you can use the long axis of the satellite and some kind of vibration damper to passively orient, say, an antenna in a satellite so that it's pointing towards the Earth. But that's on sort of a long time scale. It's an orbital time scale. So it takes, it depends at what orbit you are. So, you know, if this is, say, the Earth, and you're just a couple hundred miles above the Earth out here, sort of at space station level, then one orbit around is a couple of hours. Okay? But if you're at geosynchronous orbit, which is at about 22,000 miles. So geosynchronous orbit means you're far enough out that the time it takes to orbit the Earth once is 1 day. And so what that means is as the Earth rotates on its axis, which is one revolution is 1 day, then the satellite is also orbiting once per day. So that means that you look up and you always see the satellite. It's always there. Okay? So geosynchronous orbit is, you're here and the satellite is here, and as you rotate, 1 day, as the Earth rotates 1 day around, the satellite is rotating 1 day around, but it's much further out, so it has a lot more distance to travel. And that's about 22,000 miles. A low Earth orbit is much faster, but it's not geosynchronous. And so when we talk about sort of libration damping and passive attitude stabilization, we're talking about a relatively long time scale. So if you're willing to wait long enough, then the satellite will orient in that way. On the other hand, if you want to orient in some way other than having something directly pointed toward the center of the Earth, what can you do? Well, one approach is there are so-called reaction wheels, and this is a kind of reaction wheel. So reaction wheels, basically you have your satellite, and then you have sort of like flywheels, basically, like in the way a bus, a city bus stores energy so that it can gain acceleration, is that it puts energy into a flywheel. So a lot of these energy preserving systems for cars or other things, ideas that have been discussed are you put energy in a flywheel. So you put on the brakes, the energy goes into a flywheel, and then when you need to accelerate, you draw energy from the flywheel. And so it's basically a wheel that's spinning, and if you want to reorient the satellite, you basically slow down the wheel relative to the satellite, and then that means that the satellite is going to rotate, and then you reverse that procedure, and then you've changed your orientation. And so if you have flywheels in at least 2 directions, then you can change the orientation of your satellite by either sort of connecting up to the flywheel or disengaging from the flywheel. So a flywheel is rotating around continuously. In contrast, this flipper idea, you're just rotating by small angles, so you don't have to execute full rotations. And the reason for this is because if you're looking at microsatellites, then it's hard to micro-machine things that rotate. Okay, they tend to burn out, friction and other things end up being a big issue, whereas at the macro scale, flywheels work fine. So that's one way to reorient on a much faster time scale than an orbital time scale. And then there are other things that can be done. So for example, the Earth not only has a gravitational field, but it has a magnetic field. So you can have a satellite that basically has a coil in it. Okay, and so you energize that coil, and you have an electromagnet, and that can interact with the Earth's magnetic field, and that can be used to change the orientation of the satellite relative to the orbit. And then there are other things that can be done. So for example, you can, so here's an analogy. So, if this is a swing, and this is a person, and they're swinging on a swing, right? So you can start out just like here. You can have a satellite that's pointing towards the Earth. It's been gravity gradient stabilized. But say you want to change its orientation. Well, that's analogous because this is governed by the pendulum equation. That's analogous to a person on a swing, right? This is basically a pendulum. You have a person sitting down here, not moving. That's at theta equals 0. That's like the satellite pointing towards the Earth. But if you don't want it to point towards the Earth, what can you do about it? Well, you can do something similar to a person who's swinging on a swing, right? They start out just sitting flat, and they pump their legs back and forth, and you can get motion that way. Well, over here, you could do the same thing. So you can have, we talked about a deployable boom from a satellite. If that boom, instead of having a spring on it, has a motor on it, and you pump it back and forth, then you can basically cause the same kind of resonance that you get over here in the swing to reorient the satellite. But that, as well as the original gravity gradient, is sort of on a time scale of an orbit or multiple orbits around the Earth. But who has time to wait? So the coil method or the flywheel method is a much faster way of doing things, although it means carrying more hardware on board, which is, it's expensive to launch things. Now, of course, microsatellites are very small. That's why they're called microsatellites. And so the idea is that those would be much less expensive to launch. But we can't benefit from the flywheel idea, therefore the microflipper idea. So that's, okay. So now we're coming back to the paper again, but I just wanted to put it in context. So when parameterizing rotations, so there are many 3-parameter descriptions of rotations. We've seen Euler angles before. The axis angle formula is another way to describe rotations in space. So it turns out, so if we're looking at the unit sphere, if we have a direction, let's call it n, that's describing the axis of rotation of a rotation. So if I want to rotate an object, I can say, instead of describing it as a rotation around z and then x and then z again, I can think of it as just, it's a rotation around some axis n in space by some angle theta. Okay? So if I rotate around an axis n by an angle theta, what am I doing? Well, let me draw another picture here. So we have a reference frame fixed in space. And I have a point out here, an arbitrary point x. And if I say I'm going to rotate that point around some axis that's defined by the unit vector n, by an angle theta, then I'm going to end up maybe somewhere over here. So in other words, you can think of the original vector x as lying on a cone, a right circular cone actually. So this is a right angle. So this is a circle here. So you have this circle, you have this cone. The original vector x was pointing to one point on the base of that cone. And then when you rotate by an angle theta, you're moving over to another point on the base of that cone. Okay? So this is kind of hard to see, so let's look from this direction instead. So from this direction, we just have the base of the cone, which is a circle. We have the center, which is where this line that's defined by the unit vector n is intersecting the base of the cone. And then we have the original, if this is the vector x, then we can decompose that original vector x into two parts. Into a part which is parallel to n. So we can say x parallel to n is equal to x minus the part which is perpendicular to n. And so the part that's parallel, or vice versa, right? X perpendicular is equal to x minus x parallel. Well, the part that's parallel to n is going to be x dot n times n. So this is x dot product n times n. In other words, that's the projection of x onto n. That's this vector right here, x parallel. That's the part of x parallel to n, and the part that's perpendicular is just what remains. It's x minus that. So x parallel is x dot n times n. X perpendicular is x minus that. So it's x minus x dot n times n. And let's see, let's make sure that works. So if it works, it should be that the dot product of x parallel dot x perpendicular should be 0. So let's check that. So if I take the dot product, what I'm going to get is x dot n times n. Dot product this is x dot n squared. So this dot this is this, and this dot this, because n is a unit vector, n dot n is equal to 1, because n is a unit vector, then this dot product with this is just going to be this times this, which is the same thing. So x minus n, x dot n squared, so it's equal to 0. So that checks out. So x parallel and perpendicular are orthogonal to each other, which is what we expect. Now, the question is, what happens if I rotate around the vector n by an amount theta? Okay? Well, that's not going to change the parallel part. The parallel part is going to stay the same. But if this is my original, say, x perpendicular, which is in the plane of the base of the cone, then when I rotate that counterclockwise by an angle theta, I'm going to get a new x perpendicular, okay? And my new x is going to be my old x parallel plus my new x perpendicular. So if I can figure out what the new x perpendicular is, this is an angle theta. If I can figure out what my new x perpendicular is, then I can know what my new x prime is, and that will give me a formula for the axis angle parameterization of rotations. So, well, there are two perpendicular vectors in this that are important to us in this plane of the base of this cone. There's x perpendicular, which is what we started with, but also if we take x perpendicular, so remember n, the vector n is orthogonal, so n is sticking perpendicular to this plane. So n is coming out here. Okay? So if I take n cross x, okay, then that will also be a vector in this plane. So maybe I should draw this so that theta is smaller than 90 degrees. I'll draw it like this. Just so this is my new x prime perpendicular. Okay? Well, it turns out that I have my x perpendicular, and it turns out that this vector, the normalized version of this vector, is also going to be in that plane. Why is that? Because, and I could have taken this as n cross n perpendicular, x perpendicular. Wait a minute, let's see here. Yeah, right. So if n is coming out this way, then by the right-hand rule, n cross this is going to give me this. Okay? And so, and it doesn't matter whether I use x here or whether I use x perpendicular, because the parallel part is going to get killed by the cross product. Okay? And so, at the end of the day, what that means, so we can write this as n cross x, okay, divided by the magnitude of n cross x. So we have two vectors. That gives us a coordinate system in this plane. And so what we can write is that x perpendicular, the new one, after the rotation, is going, just like we did like the first day of class, we can decompose this into sines and cosines and say that the new x perpendicular is going to be the old x perpendicular times cosine of theta plus this vector n cross x divided by its own magnitude, n cross x, times sine theta. And so if I take that and if I add it back to the parallel one, then I'm going to get the new x prime. So the x prime, in other words, the new vector is going to be the parallel part, which is x dot n times n plus this over here. And what is x perpendicular in terms of x? Well, that was x minus x dot n times n. So this is x perpendicular times cosine theta plus n cross x divided by the magnitude of n cross x, all times sine of theta. Now, if everything worked out, let's check. This has a name, but before I tell you the name, I'm going to check it on Wikipedia, just so that I'm one step ahead of class. That was the first advice that I got 20 years ago when I started teaching, was be one step ahead of the class. So I'm going to try to be one step ahead. So okay. So this is this should be. Oh, I typed the wrong thing. So this is Rodrigues' formula. it's not exactly Rodrigues' formula. So what did I do wrong? So is this equal? Let's see here. I think this is all okay, but this normalization over here. Maybe I didn't need. No, I didn't need to do that. Because, okay, so this is the unit vector, but that unit vector has to be multiplied. It has to have the same length as this vector over here, right? So and so once you multiply by the length of this vector, then you don't need this normalization anymore. So if I want to be consistent, this unit vector over here would be over x perpendicular, but then I multiply it by its magnitude back to get that, and likewise I multiply this by its magnitude back to get that. So we don't need this, and we don't need this, and yes, this is a unit vector, but the magnitude is that. So this is Rodrigues' formula. And this can be written in a different way. And the different way that that can be written is in a matrix vector form. So we can write x prime is equal to some rotation matrix. And that rotation matrix is usually denoted as m comma theta times x. So we take the original vector x. So we have, remember, see, we have a vector x here, we have vector x here, we have vector x here, we have vector x here. So the vector x is actually appearing linearly in this expression. And whenever you have a linear expression, you can describe it as a matrix vector product. And so if we want to pull out the vector x, then what we're going to get is so we have, and well, let's just first make sure there's no more problems. So we have cosine